Your phone is charging, but there is no cable connected to it. So how can energy travel through empty space and end up inside your battery? At first glance, wireless charging seems almost like magic. You place a phone on a charging pad. Energy somehow moves from one device to another without any visible connection. But in reality, the process relies on a well understood laws of electromagnetism that engineers have been using for more than a century. Despite the name, wireless charging does not send energy through the air in all directions. Instead, it uses two coils of wire placed very close to each other. One coil is hidden inside the charging pad, and the other is hidden inside the phone. These two coils are the key to the entire process. When electricity flows through the coil inside the charging pad, it creates a magnetic field around the coil. This field stores energy and extends into the surrounding space, but simply creating a static magnetic field is not enough to charge a phone. A steady current creates a steady magnetic field. While the field exists, it does not continuously transfer energy to the phone. Wireless charging uses rapidly changing current instead. As the current changes direction many thousands of times per second, the magnetic field continuously changes as well. A common misconception is that any magnetic field can generate electricity. But a constant magnetic field does not continuously transfer energy. The key is change. A changing magnetic field can interact with another coil nearby and transfer energy into it. Without the changing field, wireless charging would not work. When the changing magnetic field reaches the coil inside the phone, it pushes charge back and forth within that coil. This creates an alternating electrical current. The phone's charging electronics then converts this energy into the form needed to safely charge the battery. This process is known as electromagnetic induction. At this point, energy has successfully moved from the charging pad into the phone without any direct electrical connection. The phone carefully manages this incoming energy and sends it to the battery charging system at the appropriate voltage and current. Have you ever noticed that moving the phone slightly can reduce charging performance? That's because the two coils need to be aligned reasonably well. The better the alignment, the more magnetic field passes through the receiving coil, and the more efficiently energy can be transferred. Many modern wireless chargers use magnets to automatically align the phone. This often leads people to believe the magnets are transferring the energy. They are not. The magnets simply help position the coils so that the wireless charging system can operate more efficiently. Wireless charging works best when the coils are very close together. As the distance increases, less of magnetic field reaches the receiving coil. This is why even a thick phone case can reduce charging performance, and why wireless chargers cannot normally charge devices from across a room. Not all of the transmitted energy reaches the battery. Some energy is lost in the coils, electronic systems, and surrounding materials. These losses are converted into heat. This is why both the charging pad and the phone often become warm during wireless charging. Wireless chargers can sometimes transfer energy into objects that were never meant to be charged. If a conductive object, such as coin, key, or paper clip, is placed between the charger and the phone, electrical currents can be induced inside that object. Those currents produce heat, which is why modern chargers perform foreign object detection. With a cable, electrical energy flows directly through conductors into the phone. Wireless charging adds extra conversion steps. Energy must first create a magnetic field and then be converted back into electricity. Each step introduces losses, making wireless charging generally less efficient than wired charging. Modern wireless chargers can transfer surprisingly large amounts of power. To achieve this, they use carefully designed coils, advanced power electronics, and intelligent control systems. Many chargers can also adjust their output depending on the capabilities of the phone. Wireless charging is not just about transferring energy. The charger and phone also exchange information. This allows the charger to adjust power levels, improve efficiency, and reduce the risk of overheating. Without this communication, fast wireless charging would be much more difficult. If wireless charging works through air, why not charge a phone from several meters away? The problem is distance. As the coils move farther apart, energy transfer becomes less efficient. To deliver useful power over large distances would require much larger systems and more energy. One useful way to think about wireless charging is as a loosely coupled transformer with air gap between its coils. Traditional transformers place both coils close together around a shared core. allowing energy to transfer very efficiently. Wireless charging uses similar principle, but the coils are separated by air and are coupled much more weakly. So wireless charging isn't magic at all. A change in magnetic field carries energy from one coil to another, where it is converted back into electricity and used to charge the battery. The process is convenient, but it comes with trade-offs such as lower efficiency, extra heat, and limited range. Even so, it's an impressive application of electromagnetic induction that millions of people use every day.